the front page really quickly, and we're going to talk about the difference in distance and displacement. So remember, we said distance was a scalar quantity. And what did that mean on Friday? That it was a scalar quantity. It means that it only needs a number. So remember, all of our numbers need to have units in science, but a scalar quantity only needs that number in a unit. And we said that displacement was a vector. It has a direction. And so we called that how far out of place an object is. That's kind of how we described what displacement was. And if you remember back to Friday, we said the variable that represents distance was a d, and the variable that represented displacement, we called it d, and we put the little vector arrow symbol over it. And so you're going to notice today that I'm going to switch that, and I'm now going to call displacement x, and it's how far out of place an object is. So really, it's the change in its position. And so I want to use x for position because if we are talking about on a graph, a lot of times that's going to be on the x-axis is where we're going to see position. And so calling it x is going to keep it consistent with what we do in math. And so displacement is really the change in that. So if you remember, we said that a triangle out front, or delta x, represents the change in position. So that's how we're going to look at displacement today, and you're going to see me use that delta x for that. And anytime we see the change in position, or delta x, that's going to be equivalent to x in the final position minus x in its initial position. So x final, or position final, minus position initial. So we worked these two problems on Friday, and I hope that you have those in your notes. But quickly, let's calculate the displacement on each. We're not going to talk a whole lot about speed when we do, about distance when we do speed and velocity. We will use it when we calculate speed, but really for physics, we're worried about velocity. We want to worry about those vector quantities that have a direction. That's really what we're going to be worried about. So let's look. A teacher walks 4 meters to the east, or 2 meters to the south, 4 meters to the west, and then again 2 meters to the north. What was the net displacement? And we said that that was 0 because this position right here was both the ending and the beginning. So if we did delta x final minus x initial, I'm sorry, let me erase that. If we found delta x by taking x final minus x initial, we would end up with 0. So delta x equals 0. Because we ended in the same place we started. And again, if we look at the football problem, the football coach walks 20 yards to the north, turns around, walks 10 yards south, turns around again, and goes 25 to the north. What is his displacement? So delta x equals his final position minus his initial position. So let's call his final position is going to be 25 minus 10 plus 20. So to find x final, 25 minus 10, because he went 10 in the opposite direction, plus the 20 he went at the very beginning. 10 is 15, plus 20 is 35. That is x final, 35. And we'll call his initial position 0. So delta x here equals 35 minus 0, or 35, which is what we found when we did it without the formula on Friday. So now let's flip to the back. I'm sorry. Let's flip to this page right here, speed and velocity. I'm sorry, I have to zoom in because my good pen has broken and I'm having to use a larger one. Okay, speed. Speed is going to be a scalar quantity. So speed is a scalar quantity. And remember, that means it does not need a direction. It refers to how fast an object is moving. And we're pretty familiar with speed. We talk about speed of our vehicles. So a lot of times we talk about how fast we can walk or run. We talk about speed for lots of different things in everyday life. So a fast-moving object has a high speed and can cover a large distance in a short amount of time. In contrast to that, a slow-moving object has a relatively low speed and it doesn't go very far in that same amount of time. And so an object with no speed at all would have 0 speed. And so our symbol or our letter that we're going to use for the variable for speed is S. And here you'll see that I have average speed. And so we would notate this by SAVG, average speed. When we talk about average speed, we're taking the distance traveled, so distance, the distance from the page before that we did, divided by the time it took to go that distance. So divided by time. And this is really the change in time. So you will see S and maybe SAVG equals D over delta T. Remember that we distance D, time that has elapsed, the change in time, and that delta represents change. So delta T. Speed equals distance divided by time. So let's look at velocity. Velocity, we said, is what kind of quantity? We said it starts with a V, so it's a vector. And velocity refers to the rate at which an object changes its position. So the rate at which an object changes position. And velocity is going to be notated by the letter V. Remember, it's a vector. And when we see average velocity, that's going to be the vector V, AVG. velocity is direction aware because it's a vector quantity. So when we are evaluating the velocity of an object, we have to keep track of direction. And that's why we're only doing this in one dimension. So we're only going to be going left and right or up and down. We will go east and west or north and south, not both right now. We might get to that later in the year, but right now we're only doing one dimension. So like we said, velocity is the rate at which an object changes position. And we said that the change in position is displacement. So displacement and the word rate tells us that we have to divide, tells us that it's going to be a ratio, displacement divided by time. So the rate at which an object changes position, displacement divided by time. So remember we called displacement delta x because it's the change in time. So V average equals the change in displacement, so the change in position, divided by the change in time. And we also said that anytime we see this delta x, it's x final minus x initial. And we can do the same thing for time final initial. Now, a lot of times your initial time here is going to be 0, and that's because we're starting with 0 on our stopwatch, and then we would start the stopwatch and get some time final, and so final minus initial is just going to give us whatever that time is most of the time, but not always. All right, let's look at an example. While on vacation, Lisa Carr traveled a total distance of 440 miles. Her trip took 8 hours. What was her average speed? So speed average equals distance divided by the change in time. So how far did she travel? That's her distance. So let's look at that. Let's highlight it in blue. So distance in blue. She traveled a total distance of 440 miles. 440 miles, abbreviation for miles is MI, over or divided by the change in time. So let's highlight that in green, the change in time. So we're going to put time final minus time initial. The initial time when she started her trip is going to be 0. And that final time when she got there, it is 8 hours later, right? She said it took 8 hours. So 8 hours minus 0 hours. So we're going to do 440 miles divided by 8 hours. So let's check that out on our calculator here. Divided by 8 hours, 55. And our unit here is mph, miles per hour is mph. All right, let's try another one. A teacher walks 4 meters east. Okay, I'm going to draw a little picture here. Two meters south and 4 meters west. This looks a lot like our picture from the problem on the previous page. 2 meters north. The entire motion takes 24 seconds. Determine the average speed and the average velocity. So speed average equals distance divided by. We go back. We had calculated her distance here, and her distance was 4 plus 4 plus 2 plus 2, and that is 12. So her distance was 12 meters, and her total time was 24 seconds there. We put that here. We added them all together to get the distance, just like we did on Friday. And so 12 divided by 24. So we want that as a decimal. So if you need to, go ahead and plug that in your calculator. So 12 divided by 24 is going to give you 0.5. So 0.5 meters per second. Going to be your speed. So your average speed is 0.5 meters per second. Now remember that when we did this problem on Friday, we found that it had a displacement of 0. So if you think about that, what is our velocity going to be? Since our displacement didn't change, in 24 seconds, our velocity is going to be 0. So V average, forget your little arrow for your vector. We're going to have 0 meters for our displacement. 0. Fill that in on your page. Okay, let's look at one more. A pitcher throws a baseball from the pitcher's mound to the home plate in 0.46 seconds. The distance is 18.4 meters. What was the average speed of the baseball? So speed average equals distance divided by time. In green, the distance is 18.4 meters. So 18.4 meters over, let's find time here, 0.46 seconds, 0.46 seconds. So we end up with 18.46. 18.46. That gives us 40. So his average speed is 40 meters per. Okay, one more here. In the funny car competition at the Joliet Speedway in Joliet, Illinois in October of 2004, John Force completed the quarter-mile dragster race in a record time of 4.437 seconds. Determine the average speed of the dragster in miles per hour. So it's wanting us to convert our answer to miles per hour, and we can see that we have seconds and miles here. But first we need to find the average speed, so let's worry about doing that first. 1/4 mile, so if you did 1 divided by 4 on your calculator, if you need to do that to find this as a decimal, you can do that. But 0.25 miles. So 0.25 miles was his distance. 0.437 seconds. I'm going to plug that in my calculator really quick. 0.25 divided by 4.437 seconds. 0.0563. So 0.0563. Let's check. And per second. In miles per hour. So what would this be in something that we can recognize? So to do that, I'm going to continue to write this like a fraction second. So I'm going to multiply by a conversion factor that tells me how many seconds are in an hour. And so we know that there are 60 minutes in an hour and 60 seconds in a minute. 60 times 60, 3,600. So there's 3,600 seconds in 1 hour. So our seconds are with units and hours on the bottom. Notice how I made sure that the seconds were across from each other so that when I multiplied, they would cancel out. So I know I'm going to have units. I've highlighted in green. That's what I want. So I'm going to take that 0.0563 number and multiply it by 3,600 times 0.0563, 202.68. Okay, he drove 200 miles per hour in that. Now that we have changed the units into miles per hour like the problem asked us to, we are finished and we have an answer that we can kind of relate to and understand. So I want you to get out your packet and go to page 3. So you should be finished with pages 1 and 2. And so page 3 starts describing motion verbally with speed and velocity. The first part is review on scalars and vectors. So you should be able to complete these on your own by looking at your notes, and your homework packet from pages 1 and 2 should help you finish those. So let's look at number 3. Suppose you are considering 3 different paths, A, B, and C, between the same 2 locations. Along which path would you have to move with the greatest speed to arrive at the destination in the same amount of time? So let's look at path A. Path A, they go straight from the beginning to the end, and they don't really make any turns or curves or get off the path at all there. Path B, they make this bent shape and they kind of go up and make a peak. And then path C, they are running back and forth everywhere. So which one of those do you think they have to move fastest along to get to the destination? So I hope that you picked path C as your answer, and then write an explanation for that there. Number 4, true or false? It is possible for an object to move for 10 seconds at a high speed and end up with an average velocity of 0. So average velocity, and remember our equation for velocity was displacement over time. Displacement, as long as you started, is going to be 0. So this one is true, because as long as in that 10 seconds they end up back where they started, their displacement is going to be 0. So you can explain that on number 5. Suppose that you run for 10 seconds along 3 different paths. Path A, B, and C here. Rank the 3 paths from the lowest average speed to the greatest average speed. So assume that they complete these 3 paths in the 10 seconds. Which one do they have to move fastest? So similar to number 3. And then rank from the lowest average velocity to the greatest average velocity. So for speed, the whole path gets to count. So on path A, they take this really long path to get back to the same point that they started. Path B, they run just straight across. Path C, down and to the finish. So which one do you think is going to have the lowest average speed? Is going to be B, because we just have this short bit right here that is accomplished. Path C, a little bit more. So B and then C. Then lastly, this long path, they are ending back where they started, but for speed, that's okay. The distance that they traveled is still longer than in B or C. So A is going to be the greatest. For velocity, we're worried about displacement. So how far out of place the object is. And if you notice here on path A, the object is not out of place at all by the end of the 10 seconds because they're back to the starting point. So it is actually going to have the lowest average velocity is going to be A. You go back to the beginning. Lowest velocity is going to be, the next lowest is going to be B and then C, because you would have to travel faster on path C to get to the end than you would have to on path B. So I will let you look at page 4, calculating average speed and distance. So you can use one of the calculators in the room or your own calculator if you have one and complete these. If you do not complete them in class, they are homework. So make sure that you have these 7, 8 completed for tomorrow. Have a good day.